I see people joining now. Okay, that's nice. Good. So let's start with the last. So I see people joining now. So let's start with the last tutorial of this course. Yeah. So today we'll be doing. Am I audible?
Yes, you're audible.
Okay. Okay, I'll just a second. I'll just share this link with you as well. So if one of you can confirm if the YouTube streaming is also audible. I think it's audible, yeah. So this is the meeting link. And I'll also share the materials that. So I see people got a bit late today. Yeah, so it's working. Great. So let's start off. So today will be the last session of this series, and today we'll be doing today, since the topics for this week is very simple, so as in, so we'll do unsupervised learning today. And what do I mean by unsupervised learning? All these things we'll be discussing today. So what does unsupervised learning mean? So say you're given some points like this and some points like this. You want your algorithm to say that there are two clusters of points. So this is the basic intuition of unsupervised learning. You want similar points to be clustered together, or similarity measure between xi and xj should be low, or rather similarity should be high if they are in the same cluster. So this is unsupervised learning. So we are not given any labels. You'll be just given data points. So you have to cluster similar points together. So we'll see how to do that. But before going to that, let's I'll do a very interesting question with you all. So to motivate the want for a k-means clustering. So instead of having a k-means clustering, so I have this problem. So we'll formulate the k-means problem a bit later. We'll also code it. So the question is, this mu1 through mu_n are the center of, say you are having one cluster here, one cluster here. So this is mu1, this is mu2, and so on. So mu1 through mu_k, these are all the cluster's centers or the centroid. You can take the average of all those points in some way to get the centroid of the cluster. So and we are defining Rik as the probability that cluster is equal to k given xi. So it is the probability that the ith point belongs to the kth cluster. So we are told to find out mu's and rij's from such that this is minimized. So what is such that it is minimized? Well, at the, so can you see why are we trying to minimize these this term? See, wow, can anyone give me the intuition? So why are we trying to? So this is the weight. So if it has a large weight, you want xi to be close to mu I, right? To make this sum smaller. If rij is large, you want xi to be closer to mu j, isn't it? And if rij is small, it tends to 0, then xi can be away from mu j. Do you see the intuition here? Somebody was asking a question. You can go ahead. So we want to assign a yeah. So that's good.
Just I agree with you in this,
Yeah.
this point.
Yeah. So we will try to make we will try to learn this mu's and these probabilities. So this is a well-defined problem. So we'll see in k-means it's just a heuristic problem, but here we have a mathematical solution that I'll be showing with you all. So this was the motivation. So we'll be trying to get the points that are closer to one another or have a high probability. They have a high probability of being in a cluster, and away from one another will have a lower probability of being in a cluster. So we want to learn the centroids of the clusters and also the probabilities that each point belongs to a cluster. So the intuition, this is the basic motivation for today's class. So we want to make each point assigned to a cluster, but here we are doing a soft clustering. This is called a soft clustering because we are not assigning it to any class. We are giving probability that it belongs to certain classes, certain clusters to be exact. But to do this question, you can see that you can see for every I, this Rij is equal to 1, right? Because Rij is a probability, right? So Rij equal to is, if you sum from 1 to k, if you sum j from 1 to k, it means one point will be in one particular cluster, right? So it's a probability density, it's a PMF, so mass function. So it will sum to 1, right? So if you have 3 clusters, a point, if you have say 3 centroids, C1, C2 and C3, and you have this point P, so you may say this is point 7, this is point 2, and this is point 1. So the sum will be equal to 1, right? So the probability of each point belonging to each cluster will be a sum. Is that okay? If there is no doubt, we can go ahead.
No doubt, no doubt.
Yeah. So this is a so can somebody tell me what is the problem? Why can't we take derivatives and just set them to 0 here? So I had touched upon it during doing SVM, but since we did not have much time, I'll just touch upon it. I'll give you a broader idea today. So what is the problem here? So why not take the derivative of this function and set it to 0? So that will give me the points where it makes the extrema points. So the problem lies in the fact that these Rij's are constrained to be summed equal to 1, right? So you cannot have any Rij. The problem is constraint on Rij, right? Rij have to sum to 1. This is the problem. So let's see how to solve such a problem. So we'll do a very nice, undergrad level question to motivate this. So let's go to this. So let's consider this. F of x is equal to, or rather let's write f of xy. So we'll have multiple variables, is equal to x square plus y square. And we are told to minimize this. Minimize f of fx square plus y square. What is the minimum value of fxy here? What is the minimum of this function?
0 plus y.
0. So 0. So both x and y are free variables. So it's z is equal to x square plus y square. So both for x is equal to 0, y is equal to 0, you have f of xy is equal to 0. So it's a multivariate calculus question. So that's why you need, those are also multivariate. So for x, so you can clearly see. So you can see, say for if you fix a z, so what do you get? What equation is it? Z greater than 0? Your class 9-10 level maths. This is the equation of a circle, right? X square plus y square is equal to r square. That's the circle centered at the origin. So basically what you have is, you have a curve like this. If anyone has a problem visualizing, so at x is equal to 0 and y equal to 0, the value of z is equal to 0. And as you increase z, you have larger circles, right? And like this and so on. So this is the motivation. So this can be plotted as a contour plot. So what's a contour plot? You just project this on the xy line. So say this is x square plus y square is equal to 1. This is x square plus y square is equal to 7, and so on. So you have an increasing circle outwards. So is this plot clear? So if you don't have, this will give you the understanding for how to derive the Lagrangian multiply. So is this okay?
Yeah, sir. Plot is clear.
Yeah, that's great. So now you see that this small circle is minimizing the plot. So if you have x is equal to y is equal to 0, this will be minimized. But now we see we had a constraint. So if we add a constraint, say gxy, such that xy is equal to 1. So if we add this constraint, will 0 remain a minimum point? 0 no longer a minimum.
Oh, yeah, correct.
Because x is equal to 0, y equal to 0, xy is not equal to 1.
Exactly.
So we want a point such that on xy is equal to 1 is a hyperbola, as we all know. This is this rectangular hyperbolic graph. So xy is equal to 1. So this is xy is equal to 1. So any point on this will give you a valid solution, but not any point here. So you will have to traverse along this curve, right, to get a solution. So you'll have to traverse along this to see where the function, this is g of x, remember that, g of xy. So you'll travel along this curve and see a g of xy and see where does it, where say g of xy, not g of x, say a particular xy, such that f of xy is minimum. So the set from all reals is constrained to xy is equal to 1. So this is the constraint optimization problem. So how do I do it? So there is a very, very nice observation. Can anyone tell me the observation? Where will it be minimum? So see this. So say this is xy is equal to 1. When will f of xy be minimum? So I'm plotting both these curves here. So this say is equal to 0.5, this is equal to 7, and so on.
So when their centers, like if you try through the center which goes through the 0, 0.
No, all these circles go through 0, 0, right? Because you have x square plus y square equal to z square sort of a equation.
Okay.
So you want, see here the function is maximized for this xy say at infinity. So x is infinity. So here also the function is maximized. Here also it's very, very high. So how can you decrease this function? So you have to travel, you will have to select points on this line, right?
Sir, your pointer is not visible.
Okay. So you'll have to select points on this line.
Right.
So when will selecting such a point minimize your function? Minimize these set of curves, f of xy. Which point will you select such that it is minimized? Will you select this point as xy? If you select this point as xy, say x is very large, infinity, so x square plus y square is also tending to infinity. It's also minimized.
That's what I said. We will select the one which is in the middle.
Middle, as in that's you are correct in some sense, but see these circles I'll try to shrink.
Yeah.
The more I shrink it, the more smaller the function becomes, right, at the intersections.
Correct.
And eventually they'll become the smallest when they'll be touching each other.
That's correct, right?
And when, if you go even further down, you will not have the solution because xy is not equal to 1 anymore. You don't have an intersection between the two curves.
Correct.
So you will only have the minimum when these two, so Lagrange saw this, that you will have this minimum only when two curves are tangent to another. So
Okay.
extremas exist at tangents, which means they have same gradient or derivative for 1D. So I'll just draw this. It will become very apparently clear once I'll draw this function very clearly. So you'll have this x square plus, say x square plus y square is equal to z. and you have another function, say this is xy is equal to 1. Similarly, in the negative also you'll have. So let's just consider this. At this point, they're touching one another, so the gradients will be, they may be in any direction. So this is the gradient of, so gradient, you must remember, is the direction in which a function decreases or increases by the maximum, increases by the maximum amount. So you can see that for this xy function increases this way. So this is gradient of x. If you increase xy, f will increase. That's the thing I wanted to say. Xy you increase, so f of xy will increase. That's why I said gradient direction is here. So it's perpendicular to the plane of the tangent. You must remember that. And this is the gradient of g of x. So can you get an equation between these two? So how will f of x and g of x be related? So it will be related as, yeah. So you'll have f of x is some gradient of g of x, right? So you'll be having these, both these gradients are in the same direction. So you'll just have a scaling factor between, just to determine them, right? So this is called a Lagrange multiplier. Is this last part of the argument clear? So
can you repeat it once more?
So when you have functions tangent to another, you see that the gradients are, they can be like this also, or they can be this way also. They can be the same direction also, but their magnitude need not be the same. So how do you scale two vectors in the same direction? So v1 is in this direction, v2 is also in the same direction. So how can you write v2? You can write v2 as just some linear function of v1, right? So linear scaling of v1.
Right.
So that's what I did. So each gradient will be in the same direction, both the functions, either in the parallel direction or the anti-parallel direction. So you'll just multiply a Lagrange multiplier, you are done with it, right? So that's the idea. So if you can g equal to c and so on. So that is the multiplying scaling factor clear? So these are not equal, but the direction of these vectors are equal. But the magnitudes are not equal. So how can you make the magnitudes equal? You just multiply an arbitrary constant to make the magnitudes equal, right? So I'll give you an example. So 1, 1 is this vector?
Yes.
And this is 1 by, say, 1 by root 2 and 1 by root 2. So how can you make v2 equal to v1?
Yeah. V2 equals to some number into something.
v1 is equal to root 2 into v2, right?
Yeah.
So you multiply root 2 with the scalars with these numbers, you get 1, 1.
Correct.
So that's what you're doing here. So
Got
the Lagrangian is defined as the gradient of the original function plus some lambda into the gradient of the other functions. This is how you define a Lagrangian.
Okay.
So not this like this. So if you take the gradient of L, you in turn end up having gradient of f plus lambda of gradient of g. So you end up having this original equation, and then you set it to 0. So that's the same thing. So writing it in a compact manner, instead of writing in terms of gradient, you write in terms of the function. So you add a Lagrange multiplier and add this way. So any Lagrange multiplier, so you can write a problem, say minimize f of x, where x is a vector. So xy, I'm clubbing it into a vector and writing x, h of x, h1 of x, h2 of x, dot dot dot, hn of x is less than 0. This is a more general case where you can have a less than sign as well, and L1 of x dot 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 Ln of x, say Lm of x is equal to 0. So these are less than constraints, they're more equal to constraints. So what can you do? So you can write the Lagrangian as, can anyone tell me what will be the Lagrangian? So for every constraint you will be adding one term, right? So it will be lambda 1, say, let us write uy hi plus vi li. So bear with me here. So did you get this? So I'm just writing all the constraint with some multipliers. Is that okay? So this is L of x uv. That's how you define. So I think there's a doubt, right? So I just wrote here this is the original function and this is the constraint function. That's what I wrote here. So for you'll have plus mu1 h1 of x plus mu2 h2 of x and so on. So that's what I wrote in form of a summation. Okay. So can you tell me that how will this be related to the original f of x function? Why I should not have written that. So how will it be related and why? So what will be the inequality between these two? So these terms are less than 0, right? From this one, all these are less than equal to 0 and these are all equal to 0. Okay. So all the LIs are equal to 0. All HIs are less than 0. So this is less than 0, this is equal to 0. So f of x will be, this right hand side is greater than or less than f of x. So you're adding a negative number to f of x. So so L will become lesser than f of x, right?
It will be negative, right?
Yeah, less than f of x, correct. Good. So that's the reason. Now you see f of x, which was a constraint problem, can be changed to a, so if you minimize, so you see right hand side does not depend on uv. And left hand side also it's true for all x. So what can I do? This is also equal to, or you can write minimum over x, L of x of u comma v. So you marginalize the x out. So this is say g of uv. So f of x will be greater than equal to g of uv. Now you see, do you see this interesting thing? This does not have x. This is called a dual problem. This will not be used today, but just for the sake of completeness, I wrote this. The second part is not useful today. So this is g of x. So can you tell me how can you get this close to f of x? So f of x we can also write as max over uv g of x, right? So the right hand side is independent of x. So you can, for all uv this is true. So if you maximize over all uv, it still remains less than equal to x, right? So from which part is it not clear? If you if anyone wants to elaborate on that. So see, this part is clear. So f of x is, L of x is L is less than f of x. So if you minimize over all x, the minimum is always less than the function, right? So minimum is somewhere here. So for all x, the minimum is always less than the function. That's what I wrote. And that I wrote as uv. And then since the right hand side does not depend on xy, I can take maximum over u and v. So for well-behaved functions, I'll not go into these. If you want to obeying Slater's inequality, Slater's conditions to be equal, Slater's condition, you have f of x as the maximum of uv, g of uv. So can you tell me what is the advantage of doing this? So this is also equal to max of uv minimum of xl of xuv. What is the advantage of doing this? So right hand side, why did I do this? Did you forget the original intuition? Because we want to remove these constraints, remove these. And we don't know to solve constraint optimizations just like that. We just cannot take every point in the set and find the minimum. That's an intractable problem. So we want to remove this and use our derivatives again. That's why to remove, see, the right hand side has no more constraints, no constraints anymore. But this has. So we can easily solve these questions, and if latest condition hold, the minimum of this function will also be the right hand side of this function. So I hope that makes sense. So let's do this question now. So I have this, concentrate on the right hand side. I have this solution ready on the left, so you can look at it on your own leisure. So I want to find Rij and mu j's. So how can I do that? So the basic idea is, so I want to find the minimum of this function. So how will I change it to a Lagrangian? So okay, sure. You can look at the YouTube video as you can, as in your at your own time. So that's not a problem. So you see, this Lagrangian can be written as I is equal to 1 to n. So I'm writing only this function. As I told you, this is f, and this is the constraint g. J equal to 1 to k, Rij square xi minus mu j. This plus, can anyone tell me what can I write? I think this is straight. So this is the constraints, right? So Rij summation over j 1 to k equal to 1 are the constraints. So 1 minus Rij I is equal to 1 to k equal to 0 is the all the constraints for over all I. So what will be the Lagrangian multipliers sort of thing? So I'll be writing it in a different color so you can understand. So this is the f, and this is lambda of g. So how can you write? So you can write this as, say I take some lambda I 1 minus summation of I equal to 1 to k Rij I is equal to 1 to n. So stop me now if you have a doubt why I'm writing this. So otherwise I'll go ahead and derive the equations which will give you the foundations for k-means. So I just wrote the Lagrangian. This is f plus lambda g. So for every I, there is this constraint that the sum of the probability being in a cluster is equal to 1. Is that okay? So now what will I do? I will differentiate with respect to every Rij and set it to 0. Okay. Yeah. Somebody had a question. Okay. So what will be the derivative of Rij here? So remember, you'll keep in mind that the Rij have to be greater than 0, but we'll see that they in turn turn out to be good and they are greater than 0 because they're probabilities. You cannot have negative. So what is the derivative of, if we take the derivative with respect to Rij? Drij is nothing but 2 Rij mu xi minus mu j, right? So it's only for one Rij you have this derivative ready. For all it goes to 0 since it's a partial derivative. And on the right hand side, you only for only one Rij you will have lambda I. Is that okay? And you set it to 0. If the math is not clear, you have, if the step algebra is not clear, you can go through this step. Later on. So if you have any doubt, I think it will be solved. I'm just taking derivative with lambda I, so you just get left with, when you take derivative of lambda I 1 minus xi and so on, so only the ith term will remain as you're taking the derivative with Rij. So this will turn out to be Rij, or say lambda I. What are the multipliers? They turn out to be 2 Rij 2 Rij xi minus mu j square. This is one thing that it turns out to be. So you can write Rij. So to find out lambda j, what can you do? So remember one thing. So you can use this constraint, right? You have to also use this constraint to get your solution, not equal to 0 but equal to 1. So how can you do that? So I take this equation, write Rij equal to lambda I by 2 xi minus mu j. So I see people dropping off. Don't drop off. You'll have a lot of coding stuff also. So once you get the equations, it will be very clear what I'm actually doing. So now I sum over all Rij from I equal to 1 to k. So if you have say n, so rather n, so this turns out to be 1 and this is lambda I by 2 xi minus mu j. So because these are probabilities, I sum over all the numbers by law of total probability, that is 1. So I get lambda I. This is your for all I between 1 to k. So you get this. So you have this term. Now, so when you take lambda I common, so you end up with having 1 by 1 2 xi minus mu j. Rather, I'll write it this way. 1 is equal to lambda I 1 by this. So what is lambda I? This turns out to be 1 by summation of 1 over 2 xi minus mu j square. That's it. So once you get lambda j, you can also calculate dl d mu j to get similar equation. So how will you do that? You take the derivative of this term with mu ij. So remember dd of x, the norm is nothing but 2x. That's what I'm using. So you'll have 2 Rij xi minus mu j. So I'm taking the derivative of this term. So I'll write it again, leave it. So the derivative of dd mu I summation of I equal to 1 to n j equal to 1 to k xi minus mu k square plus this term will go to 0, as you can see there is no mu on the right hand side. So these do not have mu, no mu. So this will be set to 0. So this is a constant, so this goes to 0. So Rij square, so you end up having Rij square xi minus mu k is equal to 0. So mu k in turn you get as Ri summation of I equal to 1 to n Rij square xi. So that's the thing you're getting as mu k. So this is what I'm writing. So now what can I do? This is summation over I equal to 1 to n. This is also I equal to 1 to n. You can clearly see that is not mu k, mu j to be precise. So you can clearly see that it is independent of mu j. So you can sum this over and put it to the right. So mu j will become Rij square xi by summation over Rij I equal to 1 to n. That's it. So why did I do this rigorous math? To show you this iterative algorithm that the k-means also does. So you see there are two equations here. So you first find the Rij's. So the Rij's, can anyone tell me what are they? So they are lambda i's by this. So lambda I we have already seen is 1 by this term. This turns out to be see Rij is nothing but lambda I by, so let me see what I've written, 2 by xi minus mu j, which is in turn 1 by xi minus mu j. I'm cancelling the 2's, summation over all I. So you see I've also got this equation. So lambda I equation I know. So this is 1 over this. So 1 by, see the extremely beautiful form of this equation. This is why I wanted to do this. So this is the distance. So you see your probability, it's very intuitive, right? So I'll show you what is the intuition. If distance is small, assigned to a cluster, do you get the aha moment? So see Rij is nothing but proportional to xi minus mu j. So this is what we expected. If for distances closer to one another, we wanted them to have a larger probability. We are having that. And this is nothing but a marginalizing term. We are normalizing it to 1. So you see the mu k at the kth iteration. These are the kth iteration. So Rij at k plus 1 will be updated this way. And now once you get Rij, you can update mu j's for k plus 1 as this equation. So you see it's an iterative solver. Once if you get a time, you try to code this up yourself, you will see. So every time what is happening, the probabilities are being assigned and you are taking replacing your cluster centers. So if you can see the math, you'll appreciate it. So you're replacing your cluster centers by the weighted average. So effectively what is happening is, as you go closer, all these points will go to a single cluster. Do you see this? And all these other points will also go to the other cluster, because you see this is nothing but an average of the cluster points. So these terms will dominate which have large Rij's. They will dominate. I just wanted to show you. So they in turn end up having these points. So they in turn sort of make a cluster all together. So you'll be making this, you'll be updating probability, and you will also update the centers. Now can you tell me, this is a probabilistic soft clustering method. K means is nothing but assigning this to 1. So the probability, you're not giving probability, you will just take the maximum of this. So K means you just see. So how I derived from soft clustering, Rij as 1 by xi minus mu j. You take the minimum j. So argmin of j. So you cluster to the nearest point, and then you take the average of all the points in the cluster. So you'll see it again. So I'll just show you here. So this is the thing we derived in soft clustering. I'll just from K means from soft clustering. So the soft clustering problem is like this. So I'll just define the problem. So this is here. So you wanted to find the minimum sort of a cluster such that this sum is minimized. What is this sum? For each of these clusters, you want to make clusters such that the distance from the points to the assigned clusters, the sum of all those distances is minimized. So something like this, if you have mu here and something like this, you'll assign these to a single cluster, these to a single cluster. If you do something different, you will not minimize the distance, but you will maximize it. So but can anyone tell you what is the problem with this algorithm? You cannot. This is an intractable solution. You will have to generate all the possible clustering problems. So what is the number of checks you need to do? So for every point, there are k options. So k to the power n is the complexity of this clustering algorithm. So it's an intractable exponential solving problem. So you cannot solve it. Even for k equal to 2, it's exponential. We're seeing the exact all the ij's. So to do this, we introduce the soft clustering technique, and we'll be using the k-means. We'll be seeing how k-means is very similar to soft clustering. We'll not like assign every point brute force to every cluster and see which of the sum is being minimized. But what we'll be doing is, we'll be doing something like this. What am I doing? So Rij is proportional to 1 by xi minus mu j. I had already told you. And mu j, say this is kth iteration and this is k plus, so it's an iterative solution, is equal to, so Rij square xi minus mu j, rather xi I equal to 1 to n. By normalizing it, you can already write proportional. Let's write normalizing, not a problem. So you see, what if I do something like this, say the arg max of Rij, I set it to 1 and rest to 0. Not arg max, max of Rij I set it to 1 and rest to 0. So can you see what will happen? So here you will be assigning j to a closest point. So you will assign I to closest cluster point. So when I set this to 1, so max of Rij, I'll set it to 1 and rest to 0. So a point deterministically defined belongs to a cluster. Comes the summation algorithm is, so I see this connection that I generated. It is a very nice connection. I don't think you'll be getting it anywhere. So this is a 2 different problems. So you can actually define k-means from this soft clustering. So k-means would be something like this. The algorithm will say initialize k clusters, then with mu1 dot 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 mu k. Then step 1, assigning Rij step. Assign xi to jth cluster such that xi is closest to it. So what do I mean by closest to it? If you have mu1 here, mu2 here, mu3 here, so if this is xi, you assign cluster of xi is equal to 1. Now I think you people will get the catch between these two. And at the next step, every mu I k plus 1, you will update as I equal to 1 to, rather I belong to cluster I, so x belongs to cluster I by mod of cluster I. So this is the size of cluster. This is average of all points in the cluster. So if you have a doubt, you ask now. So if you first of all, do you get the connection between soft clustering and k-means? So k-means is a hard clustering algorithm, and there is no guarantee of convergence. You can oscillate if points are not near to one another. So this is a side point that you must remember. So but it will eventually try to do something like a clustering problem. It will be trying to something like a soft clustering, where it will be updating each the mu's according to the assigned points in the cluster. So first of all, any questions with the soft clustering? Second, any question with the link between soft clustering and k-means? Otherwise, I'll be doing a solution on agglomerative clustering also, and then we'll be going to the coding problem. So there's another type of class. So I see there's no more questions, no questions. So then, so if there's no question, I would be tempted to, if it was a physical class, I would have been tempted to ask people, but I don't even know if people would answer. But still here, because it's, yeah, go ahead. You have a question? Go ahead.
Very intense mathematics. We are getting a field, but we'll have to go through the notes once again.
See, there's no, the math that I did is just algebra. I did not do any maths. I just took the derivative and set it to 0. Did you take this for the fact now? Once you get it as a note, you would get the derivative and algebra. But do you see these connections? So whichever is nearer to it, Mr. Shashidhar, whichever is nearer to the a cluster point, the probability will be higher of being to that cluster point. And according to the probability, you will assign the new cluster weight. So if these are the points and they have some probability, so you will assign the the centroid of this cluster according to the probability of being in a cluster. That's nothing but the expected value of the points in the cluster, right?
Right.
That's what I'm telling. So now if you just assign one point to one cluster, so what will happen? So this equation will become a deterministic solution. You will be assigning xi to the jth cluster, and this will become, these will all become zeros and ones. So here only those i's will remain such that rij is equal to 1, right? This is the point. Okay, such that you will be averaging all those points which are in the cluster and reassigning the cluster. So this is the iterative thing that you will be doing. So people introduce k-means just by saying that this definition is not possible, so we do this. But I thought that this solution of soft clustering will make a lot of more sense. So I tried to intuit it through this manner. So we'll be doing the coding, it will become very evident then. So let's do a basic now, since we have had a lot of intense maths, as you see. So let's try something on the simpler lines now. So we see something called an agglomerative clustering, or the bottom of clustering. So you are given points. So k means k has to be provided. Okay, so this is a very big disadvantage. And there are more disadvantages, but in agglomerative clustering, what I'll do is I'll cluster similar points first, and then I'll cluster similar clusters together, and then I'll be making this, and so on. And when I'll traversing this route, I'll be getting as many clusters as I want. So this is not mathematically intense also. So this is clear, I guess. So we'll be hierarchically clustering similar points, and then we'll be hierarchically recursively clustering those points to get a single cluster at the end. So I'll walk you through an example. So let's take this example. So I have 3 points given here. Say 4 points, 0, 0, 1, 1, 3, 3, 3, 0, and 3, 1. So the question is, let's use the centroid. The question, you can see the centroid link metric to cluster these 5 points agglomeratively into so use L2 norm as a measure of similarity. L2 is the distance, just the Euclidean distance, like we take x squared plus y squared as the distance between 2 points. Given the center, now let's see. So these are the 4 points, right? 0, 0. So I'll do it, you can see the math later. I'll do it independently here so that they're not confused. So I take 4 points, 0, 0, 3, 0, 3, 1, and one more point was 3 minus 1, that was, and one more point was 1, 1. So you can see that these 2 points are near, so they'll be sort of clustering. These are points are near. So how will this algorithm cluster these points? So let's make a chart like this: 2, 3, 4. This is 1. This is 2. this is 3, this is 4, and this is 1, 2, 3, 4. So let distance between point and itself is 0. So 1 and 2, what is the distance between 1 and 2? So I'll be seeing the distance. So I have 4 points. I'll be writing it down here, 0, 0, to help you visualize. 1, 1. Yeah, go ahead.
It is nothing but 3 minus 1 whole square plus 0 minus 1.
1 and 2. So 1 square plus 2 1 square. So I am talking, if I take L2 norm square, that is x square plus y square, or rather x2 minus x1 square plus y2 minus y1 square. So this is between 1 and 2, this is 2, right?
And 2, yes.
Yeah. Between 1 and 3, that is 9, right? 3 minus 0 plus 0 square. So 3 square plus 0 square. That's it.
Are you not considering square root?
No, I'm just taking L2 norm square. Square root I'm not taking just for the calculation purposes. It's the same thing, right? So positive number, square root, everything will be, it's a increasing function. So the square and the square root distance measure will be the same. They will not change. Right?
Right, fine.
So 0 and 3 and minus 1, that is? So between 1 and 4, that is 3 square plus 1 square, that is 10, right?
Right.
Between 2 and between 3, that is for 2 square plus 1 square, that is 5. Similarly, between 3 and 4, rather 2 and 4, that is, anyone? 2 square plus 2 square, 8, right? Correct. Between these two, this is 8. 3 minus 1 square plus 1 minus 1 square, 8. And 3 and 1, that is 1. Just 1, you can clearly see between your eyes. So which of these 2 points will be clustered in the first step?
1 and 2.
You miss this cluster point. So this is 3 and 4. So thus you cluster ij such that similarity between Ci Cj is minimum. So this is the minimum, right? On the table, distance table, 1 is the minimum between. So 3 and 4 I will cluster. So this is the first step. Now I'll replace it, since it is called a centroid link, I'll replace this by 3 minus 0.5, the average of these two, right? And similarly, I'll do the same math, you will see. So I'll do the math like this: 1 between 0, 0, 1, 1, 3 minus 0.5, 0, 0, 1, 1, and 3 minus 0.5. Again 0, 0, 0. This remains to be Z2, and you can see these are all some numbers that will be greater than 2. So these two will be clustered now, right? So step 1, and this is step 2. Okay? And then you have nothing but you cluster these 2 points. So now, if you cut this graph at any points, you get subclusters. So this is called a. So I had lost you people. So can you tell me from where did we lose track?
The last topic was dendrogram, the subclusters.
Okay, so if you cut this graph,
dendrogram.
Okay, so if you cut this graph at a particular node, you will be getting clusters. If you cut here, you get 2 clusters at the 2 level. You cut here, you get 2 more clusters. So this is a sort of a hierarchical clustering also. You get a graph altogether. So you can sometimes have things like this. So at the top level, you will have 2 clusters, say. This is always a binary graph. binary tree to be clear, to be exact, and so on. So if you cut it at a particular node, you will be getting a subcluster. So everything along this will be in a particular cluster, and here will be another cluster. So if you cut along this, you will get two clusters, whichever is the head of the two nodes. Is that clear why it is helping? So this is called, yeah, go ahead.
Yeah, it is clear. I mean, you are building the clusters from bottom.
Yeah. So if you cut at any node, you will be in turn getting a sub cluster at whatever level you want to. This is a complete structure. So this is almost most of the times works better than a normal dendrogram sort of a thing. Here I've also given some more similarity measures, right? So I've given you a single link sort of a thing. So we here what we did, we found the minimum distance between centroids. So what we can also do is take distance between clusters Ci and Cj in other ways. There are other heuristics present in the market and the industry. So you see, say this is the largest distance between Ci and Cj. So you mark the distance between Ci and Cj as the maximum between these two, right? So the maximum similarity between say x and j, so this is the distance that you mark. So these points say are very close. D2 is less than D1. So D1 says the max. So this is so if you take this as a similarity measure, so you'll have so you're taking maximum distances between points to separate between two classes. So you sort of have a compact sort of a setup, right? Because when distances are like the farthest is being taken as a distance measure between two points, so whenever you take the minimum of all these points, so you'll be seeing which of the clusters are the nearest to one another, sort of a thing. So this is one of the heuristics that people use, that you see the maximum distance between 2 points in a cluster. Other heuristic is loose clustering, where you see yeah, Mr. Chandrasekhar. Hello. You have a question? Okay. So the thing is, similarly you can do it for complete link also. That is also known as a, when you have the smallest distance between these 2 points are considered, and then you again take the minimum and so on. These are different heuristics that are covered in the course, so I'm not gone into details. We just did questions that may be asked in your exam, so that's why I did this question. So I have also solved a question regarding this here. So you can see the similarity I have taken to be, I'll just use this here. Try to do, you can use other similarity measure. I'm using a single link now. So you tell me between 1 and 2, distance between initial distance will be the same. So we don't need to worry about that. So leave that. So we have already done this step. So we have clustered 3 and 4. Now you tell me. So we have 3 points here. So I'll do it again for you people. So from 1 to 2, what is the distance? That remains the same because you only have 1 point, that is 2. Now to 3 and 4, this is the critical point. What is the distance between 1 and 3 and 4? This is the minimum of, or the maximum of, the distances between Ci, Cj, such that Ci belongs to 3, 3, 4, and Cj belongs to 1. So can anyone tell me what is the distance? So you see, the distance between 1 and 0.3, what is the distance? Distance 1 and 3, or I should write similarity between 1 and 3, similarity between 1 and 4. And I will take max of this as the distance between 1 and cluster 3 and 4. So what is the distance? What is the maximum distance here? So this is 1 and 4. So this point and this point, that is root 10, right? This is the maximum between these two. Similarly, between 2 and 3 and 4, you can also calculate what is the maximum between this point and between these two. These two, what is the maximum distance? This is the maximum distance. That is 8. So now you in turn end up clustering this point, 1 and 2 again. So this is how you go in a single link. In a single link, the thing is you have to do all this ij sort of a similarity measure and take the maximum of that. I think single, if you have a doubt in single link sort of a thing, you can ask me now. So single, this will actually make the clusters tight. So I'm waiting for a question. So if you have a question. So okay, you don't see any questions sort of. So the maximum distances here will be sort of minimized here. So you'll have small tight clusters. That's the intuition. So you can do both of single link and multi-link by using this summation property. Similarity between xi and 6j, you can calculate the average of all the similarity measures between ij and divide by the sum. So this will be sort of a the bit in between single link and multi-link. I see a lot of there's no more questions, so we can sort of stop this theoretical part and move to the coding problem, since people are not asking. Okay. So I'll share my screen. Where is this share screen? Is my screen visible?
Yes, sir.
Okay. So let's see. So we'll do a k-means clustering today. I think that will clear most of your queries and doubts. So let's see. So in the first block here, I have just imported NumPy, and I'll be using the iris dataset that we have used multiple times for simple problems. So this will help you visualize stuff easily. So I import these libraries. Kernel is sort of stopped. Just a second. Okay. So doing a k-means today. Let's see. So I'm importing the required libraries here, and now I'm importing the iris dataset. So we have seen multiple times in this course that the iris dataset has. If you have a question, you stop, because I'm not being able to see people unmuting and stuff when I'm sharing my laptop's monitor. So I am taking this petal length and this I've taken two, so data, the feature names, and I've taking two columns. So I'm taking the petal length and petal width as the features to classify these, or sort of features that I'll be using to visualize. So this is the data set. So this is nothing but a scatter plot diagram. So no need to worry about that. You can see the code once available to you. This will be sharing this code. So you see the scatter plot. So this is one cluster of the flowers. So let me see which cluster does it belong to. It belongs to, so blue is in the second one. So second, the versicolor. So the versicolor, setosa, and virginica. These are the three. Green is the virginica one. So these are the 3 points. Without clustering, I am using the labels in the data. Now let us see if clustering algorithm is able to find out these clusters. So let's start with 3 because we know 3, and then we'll go to multiple. We'll increase them to higher orders. So see. So I'll define some functions. So this is basic coding that we'll do. This is X is the data, and these are the centroids. So what I do is I define a distance matrix. This is the distance matrix. So this is of the form number of examples cost number of centroids. So you see I've highlighted number of examples and number of centroids. So each ij element will tell me what is the distance of the xij point to the jth xi point to the jth centroid. Is that okay? So we are trying to find out which cluster is the point closest to now. If you have a doubt, you ask immediately. So this is the nearest. So this is sort of the distance matrix that I am calculating. So I'm initializing this. Then for every ij, I'm calculating this is the L2 norm of the distance between xi and the centroid mu j. So as I told you, the ij stores the ijth position stores the distance of the ith point from the jth cluster. So you see, so you have an array. For every I, you have, say, distance 1 through distance k. So you can take the minimum of all these distances once you are wanting to do the clustering problem. So this will give me the distance matrix. So if this is the function this is the utility function helping me to find out distance matrix. And this is the function that is helping me to do the clustering. So I'll do this clustering, say, n times. So this is nothing but initialization. So initialization, you can just see initial data and initialize. So I have taken the initial data and initialized the 3 clusters to 3 random points. So see here. So the distance matrix, I'll just calculate here. So I'm finding the distance matrix here using the function that I explained above. And the label, as I told you, you see this. So the label, how will I get? I'll get by the minimum, arg minimum of the distances in the row, right? Is this part clear? So I'm taking the arg min of all the numbers in the row. So that will give me the position, that is the cluster that along which the distance is the minimum. So that's what I did here. So if I'm going fast, you stop me. So this is the arg min. So this is giving me the cluster levels. Get the cluster level indices closest to the cluster. The columns are shrink now. So you have for every data point one number now saying. So now we have a single number for every data point which indicates to which cluster the point belongs to. So now we are seeing, what am I going to do? I am going to take the average. So this will do the repositioning of the centroids. What is the centroids? As I showed you from the beginning of the class, they are nothing but the average of the points that are belonging to the cluster. That's what I'm doing. So squeeze for the jth centroid is finds all the points that are belonging to the particular cluster, and it takes the average along the vertical axis. Here we took along the horizontal axis, shrink the columns. Here we shrink the rows to get the ijth component of the. So this will give me the coordinate of the means of the centroids. Centroids according to the redistribution. Okay, so this is all about k-means. So this is why I told you it's very simple algorithm. So you now again iterate over all this k. You keep on iterating, and at the end I'll be returning what are the labels that the function has learned, and these labels may not be the same labels that were initially. So these are different labels. This is you did not use any label to train these labels. So even if you are not knowing the initial labels, you would have some particular clustering. These are cluster labels, not the versical or virginical labels. Just to be clear about that. So I'll return y just to cluster these points. So now you see, as we had here, the algorithm, k-means algorithm is doing pretty well to find out that this is a cluster, this is a cluster, and this is a cluster given k equal to 3. And now I did the experiment for k equal to 5 as well. You see, here you find a cluster, here you find a cluster, here you find a cluster, and here you find a cluster. So now let's do for number of clusters lesser than k. So here you will see another example where it is 2. See, so as expected, these points formed a cluster as setosa and virginica is close to one another, and virginica and versicolor are close to one another. Setosa forms a different cluster. Is the code giving you the intuition that was missing in the math? Can anyone slightly unmute and respond? I can't see anyone, so it will be useful if anyone responds to help me know that I'm there in the call. So I hear no one. But see people there.
No, this looks good.
Okay, so you can see this code, and now this is, you'll also get the link to the code if you want to play around with it. You can play around with it, and that's so far from my side. And if you have a question, I'll share my if you have any questions, share my link I'll share my tablet again, so to answer them. So because this is the last class that we had, last tutorial, so I really enjoyed taking this set of tutorials. I hope that I could put forward something useful to you people besides the lessons that were taught, maybe instill in you some understanding of basic machine learning to take it to the next level when you do an advanced course.
Thank you for your sessions.
Thank you, man. Thank you very much.
Thank you. Thank you very much.
You're welcome. You can sort of write to me if there is any doubt you have. I'm just giving you can share it with, before your exams and all. So that course TS will anyways help you, but anyways, any problem regarding my part, whatever I have done, so you can go through my videos as well, and you can, the YouTube links will all be shared, are all shared with you people, so you will be getting those. So, and then you can just tell me if there is anything regarding my topics that you wanted to clarify. Okay, all the best for your exams. If you don't have any questions, we'll stop.
Thank you again.
Okay, thank you. It was a pleasure teaching you all. Thanks.